it. Actually, real quick, problems with homework 2. People are still having some compilation and stuff like that. Keep posting on Piazza. It's finicky. Compilers often are. A bunch of people, I think, like myself included, I was working on it one evening. Everything was good. I wake up in the morning, stops working. Didn't, exactly the same command. Xcode updates in the middle of the night, and after, everything changes. So yes, it sucks. We'll keep debugging as we go along. Homework 2 is due November 2nd. We'll hopefully have homework 3 out that same day so that you can get started on it. It will be entirely OpenCL. You don't need to use Odyssey. We gave you access. You've been introduced to it. If you don't have OpenCL, we won't force you to use Odyssey. If you don't have a very good GPU and want to use it for final projects, or if you need it for homework 3, then it's there. But if you can run the test.py from this repository, let's go to FastRec, github.com FastRec. This is the one that the speaker had there. If you can run test.py just in your normal Python after installing OpenCL, then you should be good. If you want help installing OpenCL on your machine, post on Piazza. We'll try to straighten you out if it's not already there. It's built into the Max OpenCL 1.2, and so you just need to do a pip install. Final projects, keep sending ideas. The proposals are due the 6th. We will get feedback to you by the 9th, which is, it's over a weekend. Our job will be easier if we hear your idea first and can give you some pre-feedback. That'll probably just result in us saying, great, sounds good. The risk is if you send us something on the 6th and we haven't heard anything about it and it's not suitable, we're going to say this is not suitable, you need to come up with something else, and you're going to be using up time that you could be working on your final project or homework or whatever, working on your idea for your final project. Which one? 6th. The web page, the class web page says like the 1st or something, but it's this final, just the idea, the proposal, something by the 6th. And we'll give you a yes, no, or feedback, adjusted in this way by the 9th. Expect to write up just like a one-page thing with the names of who's doing it, a brief intro to the problem. If you're looking for ideas, look over particularly previous years from the projects tab on the homepage. Please, talk to us early. If you're looking for teammates, talk to us or post on Piazza. There's a thread, I pinned it this morning, I forgot to before. If you're looking for a teammate, have an idea or anything like that, post in that thread. Anywhere from 2 to 4, 2 or 3 is probably optimal. Single person projects are possible with a good argument why. So you can propose that to us, but also do this early, okay? All right, more OpenCL today. Same URL. I'm not going to actually talk about the code. You don't need to be looking at the code for this one. So just to review, though, in OpenCL, the CPU is in charge of all the scheduling, all the memory management. Basically says what happens when on the GPU. GPU just handles very low-level scheduling of threads and work. When you launch a task in OpenCL, you usually launch it with a very large number of threads, which run semi-independently, broken up into work groups, which do run basically together. And synchronization is only possible at the work group level. So you have no control over which group of threads runs when. You have no control, no really good way for them to communicate across groups. You can only work within groups. So you're limited in what sort of parallelism, particularly things that we've talked about before with locks and communication using queues or things like this. Those are generally not available in OpenCL. All you have are tiny work groups. Those can communicate with each other, and then the rest of the problem. But you don't control when those groups run, so you can't even do in order sort of computation in these large processes, okay? So we talked some about the global and local sizes. When we launch a kernel, we give the global size, basically how many threads do we want to launch? And a local size, how large should the work groups be? How should we break this down into small subtasks? I don't know if I mentioned it, but if you specify the local size, it has to evenly divide the global size. In OpenCL, you don't actually have to specify the local size. You can just pass none for that argument to the kernel launch, and it tries to find something optimal. I think it still will have to choose a local size that divides the global size, so you have to be careful with things like a very large global size being a prime number. I haven't tested this, so you can pretty easily. Local size does have a limit on how large it can be, depending on the hardware that's being targeted. We'll talk next lecture about finding out these limits. But in general, something between 16 and 128, usually a power of 2 and usually a multiple of 8, or a multiple of 8, is preferred. Just because if you're targeting a GPU, it's almost certainly got 16 or 32 work units underneath. And both of these can be 1D or 2D. I want to start talking about 2D because a lot of the problems that are interesting are going to be image-based or involve arrays of some sort. So we want to do some sort of image processing on a 10 by 10 image. Okay? We're going to launch groups of 4 by 4. What's our global size going to be? What are our choices, right? Sorry? So this is a reasonable choice for a local size. Another one would be 8 by 8 or something like that. But we want to choose, our local size is usually constrained and we want it to match the hardware. We want it to be 16, 32, something like this. Our global size has to cover the input. Right, so for this, we need to get a thread per pixel. That's the sort of standard OpenCL model, a thread per input or output value. So we'll choose a global size of 12 by 12, which is big enough to cover the entire image, but now we have some complications, right? We have a bunch of threads that are operating outside of our image. We're going to have to mask these off. We saw an example of that previously in the 1D case that we looked at when we were looking at just multiplying two vectors together element-wise. So here's a kernel that does just a simple add two images together. Okay, everything should look familiar from last time. We have the kernel declaration, the name of the function, some global pointers to where the memory are, where the images are in memory, and then the width and the height. And then we fetch the coordinates out of our thread. We're going to launch at least one thread per pixel. We get the coordinates out that we're asked to operate on. And then we have this logic here, which is make sure that we're actually a thread that lands within the image. Right? So going back to the picture, we have to make sure that we're in this upper left quadrant, not one of these threads. What do those threads do while the rest of the threads are working? They do nothing, they just sit. So if any threads that don't pass this test, remember the ALU or the GPU picture, when we have a test like this, some of them will just get a some bit set that says turn off until we get to this point. And so they'll sit while the rest of them do work. You're going to see this logic when we do any image processing or any array-based work where the array can vary in size. You'll see something like this. Make sure that we stay within the bounds of what we're actually asked to work on. Almost surely you're going to launch more threads than actually cover the image. And there'll be some waste there, but if the image is large, it doesn't matter so much. Is this clear? What's going on? We're selecting the valid area. Because of the constraints of the system, the global size has to be a multiple of the workgroup size. Right? This is true in 1D or 2D or 3D, whatever. The global size has to be a multiple of the local size. The local size should be a power of 2 divisible by 8 to maximize the hardware. And may be constrained to this depending on the hardware. And so we have to stack up enough work groups to cover the image, and that means we may overflow. Okay, there's another piece of code I'd like to talk about here. If we're within the bounds, we choose an offset, and then we do this single dimensional indexing for the output and the two inputs. And not everyone has probably seen this before, if you haven't done image processing in particular, or low-level image processing. So we need to talk a little about image coordinate math. This will be, I work with images, a lot of GPU workers with images. There are other things you do, but one of the things they're really good at is image processing, just based on how they're organized. Yes? Exactly, so looking at this code, we have to do this because you can't pass, if you know the size of your array, then you can do it. You can pass an array. But when you're dealing with arbitrarily sized images, when you're dealing with them at this level, are passed as pointers in width and height. Sometimes maybe strides. The NumPy arrays are more complex. But in general, when you're talking about a single linear image, this is how you get it. You get an array and an address in memory and a width and a height. And that could be arbitrarily sized then. And you just have to deal with, you have to do your own math for figuring out where things are in memory after that. So we'll talk about that because you'll see more of this in the homework. So we're given a pointer and a width, a height and a width. Basically, these are our inputs, where to start and how big the image is. And we need to do something like operate on pixel x, y. So images in this low level, adjacent pixels in X are adjacent in memory. Okay, so when you load up an image or capture it from a camera or anything like this, then it runs across in memory. Okay, so the offset of pixel 1 or the first pixel to the right is just one element over. And then when you get to the end, it just drops down to the next row. So adjacent rows are adjacent in memory, but the same pixel in the same column are then separated, or the adjacent pixel in the same column is separated by W elements. And so that's where we get this offset. Pixel at XY is however many rows we've stepped down times the width of the rows plus the X offset. You'll see this again and again if you do image processing in OpenCL or CUDA. This is clear. I don't want to go past this until everyone understands it. Okay.
So axis to the right lies down?
Yeah. So nothing is ever simple. Right? No, this is exactly, if you're used to NumPy arrays or matrix math or anything like that, they're indexed in the opposite order. Right? XY. Instead of XY, which is image indexes, it's YX, which are rows, columns. So luckily they're still both indexed from the upper left as 0, 0, which is not the same as if you're plotting. So no coordinate same, and then if your project involves OpenGL later, it could be arbitrarily flipped again. So NumPy arrays, when you're dealing with the data itself, are indexed like a matrix, which is flipped. But you'll also see then some weird things like you'll sometimes see array dot shape, something like this, global size equals the array shape ::(-1). Because the global size wants to be in the opposite order, so you do this you take the shape and you reverse it. So this sometimes happens. You'll see this code. It's just doing this, trying to get the row column order in whatever is expected by the hardware relative to NumPy. Is that a convention in the image processing world? It is, sort of. It's not Fortran, it's not C, it's just, I think, so the left to right, I think the image indexing from being X first is from plotting, X and then Y, or, usual coordinates. I think the upper left is because TVs scan that way. So image, when you're putting an image on the screen, it used to be, you would point to a piece of memory and scan it out, and the memory would be trying to keep up with the beam being cast. And so the fastest way to do that was to store it in the order that the beam was going to move. So if TVs had gone from the bottom, everything would be beautiful. Actually, if they'd scanned like matrices, then everything would be wonderful, but they flip and they go from the top, so. Okay. Yep.
Can you go back to the code for one more minute? So what's the next line? Offset out, offset this, offset this.
Okay, so the images are all the same size on this, in this algorithm. And so this is how, if this is a pointer, which it is, and that's how we're going to get images, then this is just take the pointer and move this many elements forward and read that memory. Or if you're assigning, write that memory.
So you're just adding the pixels to the images here?
I'm just adding, sorry, what?
Pixels to the images here?
I am, that's all, this is just gonna add 2 images, yeah. So this is the X comma Y pixel of image 1 plus X comma Y possible and store over there. Okay. Any more questions about image math and stuff? There'll be examples. There are plenty of examples online as well. You'll just see that sort of code pattern. I want you to make sure that there are a bunch of extra bits that are basically boilerplate that I want you to make sure you understand. Okay, let's talk about a 1D filtering algorithm. I've got some noisy data. I want to smooth it out. A simple algorithm is to repeatedly take a pixel, add its neighbors, and then, sorry, it shouldn't be neighbors over 2, it should just be add neighbors, right? Add my neighbors to my value, twice my value, and divide by 4. So basically, central pixel gets twice as much weight. It's not critical. Basically, I'm gonna take my neighbor values and average them into my own with some sort of weighted sum. So if I do this, 5 times or so, I get from this blue line, I get this red line. Okay, here's an implementation in OpenCL. I'm gonna operate again just on every pixel. I'm gonna have some logic to make sure that I stay in bounds. I'm not gonna talk about that right now because it's not important, but I'm basically gonna take my same thing. I'm 1D now, so I don't have an offset, I just have an index. I'll take my left neighbor, twice myself, and my right neighbor, add them together, divide by 4, repeat this some number of times until the data is smooth. Okay. How many memory reads if I have n pixels? 3n. Exactly. It's a little inefficient, yeah? Computation is basically free, particularly for simple algorithms like this. This is going to be bandwidth limited, right? There's not a lot of, right? There's very little compute. 3 adds, 2 multiplies, a fixed length divide, which is going to be very fast, or power of 2 divide. So this kernel is going to be bandwidth limited. On a very large data set, it's going to be just limited by how fast we can read the data and then write it back. Actually, so 3 reads and 1 write. We can't get away from the write. It's not very efficient. And remember, we don't have a cache. We're on a GPU. We have no cache. If we read from memory, we read from memory. We go all the way. We'll stall until that point. Even though in a CPU, this would be basically optimal code. We would loop and do this in a small inner loop, right? We'd read across memory in a coherent fashion. when we read back one element and forward one element, the data is almost surely in L1 because we just did the previous element before, right? But now we're in GPU land, and every memory read is an actual memory read and takes the full time, more or less. We'll talk about how that's not true. But in this case, we're going to do 3 reads per element. It's not going to go very well, or it's not as good as we could do. And this is where we start to talk about using local memory. So we don't have a cache. We do have a cache. We just don't have an automatic cache. So local memory is on chip on the GPUs. So we have some amount, 64K or something to divide up. But we don't get it automatically. We don't get it for free. We have to allocate it at kernel launch. And then it's shared within a work group. It can be used like cache if you can read a value into local memory if you know you're going to be reading that same value again and again, and for some reason can't store it in a variable. Or as a shared scratch pad. It can be used for communication within a work group, right? So again, it's shared within a work group, but not available to other work groups. So you can use it as shared scratch pad or a place to do partial work. Yep. So so you can't, you're asking, so you're saying, sorry, you can't write memory to the local scratch pad at once?
Yeah.
We'll talk about that. It turns out you can. The GPU can. So you can get can it initialize it quickly? Let's hold this question until a little bit later. I think you'll get the answer you want. You can, if you just think about memory reads, you can use it to reduce them. So here's the same algorithm now. We're just going to do smoothing. Using local memory. Again, local memory is fast. It's like L1 cache speed or L2. It's very fast. It's on chip. It's just limited in space. So same thing. Now we have this temporary buffer. We specify local to tell the kernel where it's going to be accessed. And then we have this LX index, which is our local ID. Do you remember the subdivision of work groups? Let me redraw that since I forgot to put in a slide. We have some global work group size, split into local groups, work groups. Our local ID is our offset within our work group. So this one would be 2, 0, 1, 2, and they repeat, 2, 3, 4, 2, 3, 4. Our global index is, this would be 4, 5, 6, 7. So this is global, and these ones are local. Okay. So we get both our global index, the element of the input that we need to work on, and our local index. And we do this pre-cache. We have the same sort of logic here. We need to check bounds. And we set our temporary buffer at our local index to the input that we're going to be using at the global index. And then down here, we use LX and the temporary buffer. So your question was, how can we load the local memory efficiently? So this is how you would do it. Each thread loads one piece of the local memory. So each thread does one read from global and writes to local. But then because they're shared within the work group, you can use the data that your neighbor wrote efficiently. So these reads go to local memory very fast. That read goes to global memory, and it's slow, but we have to read it at some point. Does that answer your question?
So like boundary case where the local is where it's out of bounds.
Is there a boundary case where the local is out of bounds? Yes, there has to be. The logic is going to be more complicated here because now we have a couple of things. One, we have the overall, am I in a valid area? Am I less than n, right? All right, so I have to check that before I read the input, am I actually reading a valid input? Then there's also boundary case, right, where my local memory doesn't extend, and I have to handle that in a special way. I already had to do something there. I just kind of, I swept it under the rug, now I have to sweep more under the rug here.
Oh yeah, that's true. Like the previous one was wrong. That was not considering the boundary.
Yeah, the previous one wasn't doing the boundary, it was just saying, okay. So there might be special logic for the edge cases where I repeat a value or something like this. I have to do the same thing here when I start using local memory. I have to do that same logic. It's just more complicated because now I have to do it in two pieces.
Wait,
Oh, sorry. No, go ahead.
do you really want to copy? Like, I understand for the
Oh, it's not the same.
edge case. Like, I understand that we copy, but when we actually add the value, but in another work group, I think we should get the value.
Oh, we can't get it from another work group. So you're saying when we, in the boundary case between two work groups, so we want to fetch from the other work group,
Yeah.
we can't fetch from another work group. There's no communication between work groups. They can both go to the same global memory.
To copy the same value on the right? Like, it sounds wrong. Like, we're adding something like that.
No, so this is the thing. So we would specify how should this behave if we had infinite processors. Our work group was infinite, right? So what should it do at the edge of the full array, right, n elements? And maybe the answer is, okay, for the edge elements, just repeat the value,
Yeah.
right? So this is a perfectly valid thing to do. Then you have a bunch of logic here that has to make sure that still happens, even when you break it up into work groups. So it's more complicated. Yeah. And what you're going to do is could get ugly.
Do you have to loop over temp, or?
Do I have to loop over temp? There are no loops. I mean, well, there are loops. Loops exist in OpenCL, but we have a thread, right? The concern is, as long as we make sure every value is read into temporary memory, and then we deal with boundaries correctly. So this happens in every thread, every inbound thread. The same way, right? We didn't loop here, correct?
But how do you assure that LX plus 1 is there before you're accessing?
Ah, you have skipped 2 slides.
I see.
Well, first, how many global reads? N instead of 3N, so 3 times. It'll go 3 times faster. This is not gonna be limited by compute. This is gonna be limited by bandwidth, so doing this 3 times faster. With more logic, even with the extra computation to figure out edge cases, things like this. So how do we make sure that our neighbors are ready? Right? So the question he asked is, do we know that LX minus 1 is there before we get to this code?
Well, if you're calling them in order, yes.
If we're calling them in order. There's no order.
So you can't even guarantee that.
OpenCL, there's no order, right? There's, depending on the hardware underneath. Right? We could be targeting a CPU and then it might choose to order them, but it could choose to order them in reverse order. But anyway, there's no order that works because we want our left neighbor and our right neighbor. Right? So there's no order that we could do this a pixel at a time and go through the whole computation, right? So what do we do? How do we make sure?
Because what we're computing, we don't reuse that. Like, out is not reused. Like,
Out is not reused.
So, what is the question?
So the question is, okay, so we've got a bunch of threads that come in here and prepare our local memory for this step, right? Our local memory has to be ready for this part to work, right? But they're just a bunch of independent threads as far as we're concerned. How do we make sure that this happens? How do we make sure that the temp buffer is valid before we get to here? That's a couple slides forward, but we'll come back to that. Right, if you were doing this if you were in Python land, or even Python OpenMP land, and you launched 1,000 threads to do 1,000 pixels of work like this, if you launched a thread per element, you know this would not work, right? It's gonna go in, it's gonna load up temp in some random mass order, sorry. It's gonna load up temp in some order, and then it's going to process before temp is ready. It's gonna go on through there. Okay, we'll come back to that in just a sec. How do you actually allocate local memory? This is what it looks like in the Python, in OpenCL, PyOpenCL. You just pass another argument with using local memory, and you just give a local size. Actually, that's wrong for the example I showed. That should be times 4. But you just give a size in bytes, and it allocates that. Remember, it becomes part of the context. Right? Small contexts, the context of the thread is what it needs to run and to be suspended while another thread runs on the same hardware. If you make the context very large, the hardware can't hold a lot of threads. And our only hope for latency hiding in OpenCL and GPU land is lots of threads. So if you allocate a lot of local memory, you'll get it's called occupancy in GPU terms. You'll get low occupancy, you get poor latency hiding, and it'll go slower again. Okay, so what's missing? Exactly, this is exactly your question. How do we make sure things are ready? We really only have one synchronization primitive. Well, there are atomic operations which you can use for synchronization. But this is the other thing that you'll see. You'll see barriers. So barrier says, everyone in my work group, run to here, and then stop until everyone catches up. And then you have to pass this argument. I don't know what CLK stands for. OpenCLK. Local memfence. Local memfence says, make sure that local memory is valid, that everything that I've read and written, or all my reads and writes are flushed to local memory at this point before any of us go on. So this is how you make sure that things are ready. Okay, you'll see this. The CUDA equivalent is sync threads. For those of you who've actually seen CUDA or are thinking about using it. And as we said, we're also missing a bunch of logic for edge of workgroup. The typical thing would actually be to put in some extra buffer space on the edge of temp, an extra element on each side, and have your logic up there load in extra values from outside, possibly dealing with the 0 to n problem as well. And then this logic becomes simpler. Then you know that your temporary buffer is valid for yourself and one to your left and one to your right for all the points. Questions about the local memory? Is your temp size the same as your no, your in count size? You mean n there? So n is the argument there for, is the temporary buffer the same size as the full input? No, it's the size of my work group or slightly larger in this case. So the local memory is allocated, why don't I make it just 3? Just, one before, one after, and myself. The local memory is shared within the work group. So it has to be, in this case, where we're using it to load up a value for each element in the work group, it has to be the size of my work group. I could make it slightly larger for those buffer things, so to simplify my logic when I'm dealing with boundaries. But in this case, I'm getting a shared space just large enough to hold the work that I'm going to do in my group. And then all of my group will work together to prepare that space in that first part. And then after that, we can just use it all together here after we make sure that we're all done. Is that clear? I'm trying to think of a good analogy for this, but nothing in particular is coming to me. So you first.
Go over again how that memfence fixed copy record is like that.
So if we were to run this code for 1,000 threads, we were processing an array, if n were 1,000, and we think about this in, not necessarily thinking about work groups or anything like that, but we just run 1,000 threads independently. One of the threads are going to come through and load up the temporary buffer, get the scratch pad ready, right, the local memory ready. And then some of them are going to continue right away. right? And they're going to start accessing, their value is going to be fine, right? Their central value, right? Because the thread that writes this value has already gotten the correct one. But there's nothing to say that this thread or the thread that writes this value or this value have finished by the time I get here. So if I allow threads to just continue through, if I don't put something there, there's no guarantee that the temporary buffer is ready by the time this other code executes. It doesn't do, it's stronger than that. It doesn't just say anything about the adjacent threads. It says my entire work group will get to this point. We'll all run forward till we get here, and then we'll all continue. So it's basically, you know, a big room of people preparing the workspace. You just wait until everyone, you know, I'm ready, you know, everyone puts up their hand. When everyone's hand is up, then you all go on. Which also means you can't use it inside an if clause or other places. If you call a barrier inside, you know, if I had this barrier inside make sure I stay the test with inbounds, right? There are a bunch of threads that aren't in bounds. And so they're just idling, right? So if I did this. Whoa, it's not space. This is bad. This is everyone that's in bounds, stop here and wait for everyone in my work group. If any of your work group is not in bounds, it'll just wait indefinitely.
So then, is that barrier per work group or for
Sorry, is that?
barrier applied per work group?
That barrier is applied per work group. There's nothing beyond work groups. That's the only, you can't talk to anyone, you know, they're the other work group, we're in competition with them or something. And they're run totally out of order, so you couldn't necessarily communicate at all. And they may not even be able to be preempted. They may have to finish everything before even another work group can appear.
So is the work group like the row then, or image?
The work group is a so if the work group here, or if we're talking about this case, which is just a 1D processing, the work group is some subset. Right, so there are two work groups if we set the local size to 5, which is a poor choice, but if we had this where n is 10 and our work group size is 5, then this is one work group. And their local buffer would be private to this group. And there'd be a second work group.
But then is the first pixel the second work group, or are they saying?
So the problem here isn't this pixel, right? This one wants to read this pixel, and this one wants to read a value that's not there. Yes, that's a problem. So you'd have to have special logic in here. Maybe down here, this checks, am I in the condensed part? Am I pixel 1 or 2 and n minus 1? Or sorry, order the size, right? I could either do this code for right, I could use that code for these. And then this one would have to do something special because it's out of bounds. And this one would have to maybe go to global memory again. Or maybe I make maybe we'll talk about that. Maybe I'll talk about this some more, about how to actually solve problems like this. Maybe I make my local buffer one larger on each side, and my logic for initializing the local buffer gets more complicated. But I make sure that every pixel here can read each side, right? Here and here. This is what I prefer. You do a little bit of extra work up front to simplify what's more likely. What you're doing here is probably the more complex operation than actually initializing the buffer. So I prefer to spread out the complexity rather than folding it into something that's already messy. So I do a little bit more complex work to initialize a slightly larger buffer to simplify my code here. Why is it bad to put the barrier inside a conditional? So everyone in my work group is going along. They hit that if clause. Some of them are out of bounds. And basically say, okay, well, I don't do anything until we reach the end of this if clause, right? Because that's how we deal with these multiple, how if clauses are handled in GPUs. Some of the computation just goes to sleep. Doesn't do anything until basically a flag is cleared and we reach the bottom of this computation, okay? So some of them are going along and some of them are idling. And the ones that are working hit the barrier instruction and say, okay, we stop until everyone is here. Everyone still includes the threads that have gone to sleep. And so they stop and wait. And these are just sitting there. They're not, like, it's deadlock, basically. One of them is waiting for everyone to reach the end of the if clause. Those are the ones that are idling. And the other ones are waiting for everyone to reach the barrier. But the ones that are idling will never reach the barrier. So they're each waiting on each other. And it just hangs. Doesn't do anything. So anything like barrier, right, let me put it back anything like this needs to be in a part of the code that everyone executes in your work group. So you can put it inside an if clause or something else as long as you make sure every thread hits it and is guaranteed to hit it. You can put it inside a for loop. You can put it places like this, but you need to make sure that that no one's going to be left behind. Is the context the size of a work group?
So like the local memory of a work group?
The context is the size of your registers. So if you've got a very complex, basically the live registers that are needed for the computation. So if you've got a very complex computation that involves a lot of variables, your context increases, right? Because at any point during that computation, you might need to suspend and for a memory read or something like this.
So it's a more abstract.
It's more abstract. It's basically, if I cut the computation at this point, what do I need to store to make sure I can start back up at that point? So it's, yeah, it is more abstract than that. You can get information about it from the OpenCL compiler. I'm not sure if you can get it from Pythonland, but we'll check.
You said that we can still write it in if statement, but then we would need to write barrier in the if and also in the else.
Yeah.
Would it work if we do that? Would it consider
Ooh.
the same barrier?
I'm not sure. It depends on I'll have to check the compiler. I believe so. I think it just turns into basically an assembly instruction, but I'm not going to say yes to that.
Okay.
In general, for your own sanity,
We don't put it.
don't put it in an if thing, yeah. Okay. All right, so the other thing, we talked about edge of logic. You can also just call memfence, but this is an out of order speculative thing, which we won't need to deal with. But you'll see, if you start looking up the documentation on barrier, you'll probably see memfence. Don't worry about it. It exists. It's something that's sort of for when OpenCL is targeting a CPU rather than a GPU, where you have out of order speculative writes or speculative execution and reads and writes. It's a holdover from that more than anything. All right. We'll talk more about this as well. On the GPU, when you access global memory, regardless of how much memory you ask for, it's going to read back something like 16 and 32 adjacent floats. 32 on NVIDIA's hardware. You ask for one memory, you're paying the price for 32. That's just what you get. Threads and workgroups can share the result implicitly. If you read scattered data, then you get serialization. So you could be, if you read something out of the wrong order, it could be 32 times slower, right? You could have 32 threads running in parallel, which is at the hardware level on NVIDIA. They each read 32 memory addresses. It's 32 times slower if they're scattered than if they're all in a row. So try to do coalesced reads. Try to read memory in contiguous blocks across threads within a work group. So good, thread n in a local group, work group, reads data n. That's fine. Bad, thread n reads some widely spaced element. And remember the layout direction when you're dealing with images. So going back to the code, thread X is reading in X and then also writing out X. So thread 0 and thread 1 are dealing with adjacent memory. And so that read there, all n threads in a row, that's one read. Right, 32 if we're talking about NVIDIA hardware. So this is what a coalesced read looks like, coalesced memory access. If I had some offset there, if I were reading every fourth element, trying to do striding tricks, it's going to be slow according to how much I stride by. On older hardware, it has to be explicit, thread for it to work. Thread n has to read offset n. Thread n plus 1 has to read offset n plus 1. Newer hardware, as long as you're reading within the same bank, it can be a little bit, it acts like almost like a very sort of cache line behavior, where it just has one cache line that is there and then gets replaced. So if you read adjacent memory or nearby memory, even if it's out of order, it still works. But most hardware is still in the older land. And this is called coalesced reads. We're in GPU land. Memory is the bottleneck, almost always. So this becomes your focus for optimization. How am I accessing memory? Am I accessing it in a coherent manner? Am I accessing it in a way that's efficient? To maximize, because this is also where GPUs shine. They have 10 times more memory bandwidth than CPUs or something like this. If you can read that, if you can pull data across that bus quickly, then your algorithm can go much faster than on a CPU. Right, oh, here we go, I didn't go back. So that's a coalesced read. You should try to do something like this.
What's the speed of reading from local memory versus global? Do a rough number.
It's like a 40 times faster. So what's the speed difference between local versus global memory? It's around 40, I think.
Like an addition or something relative to that? So like on the same
So
order?
relative, so how many cycles does it take to read global memory? It varies by hardware, but I think it's similar to cache, so it's like 2 to 3 cycles or lower.
So it's on the same order of magnitude as that.
Yeah, I believe so. I would have to check the hardware specs, but it's on the order of a L1 cache. All right, next time we'll give you info about GPUs, querying about kernels too, if I can find if it's actually possible in OpenCL. I'm not sure how much support there is there. We'll do some more about multidimensional kernels and these boundary problems and dealing with them. And benchmarking, just looking at timing. How do you get information back when you run stuff in OpenCL? All right, so try to get OpenCL installed. Test it on your own machine, because if you don't need to use Odyssey, there's no reason to do so. It doesn't necessarily need a GPU, though it's best if it is, because then you'll see the performance increase that we expect. Final projects, post on Piazza, talk to us. Yep. So the test.py reports some timings for transferring data between CPU and GPU, and then within GPU bandwidth. You should hopefully see higher numbers for the GPU bandwidth. If not, then it might be targeting your processor instead of the hardware. It should print out which hardware it's using. Okay. All right, thank you. See you Friday.